Okay, so what we're working towards here is graphing these things and finding out all the information. So if I said, here's f of x, just find the domain, find all the asymptotes, find the holes if there are any. That's the new stuff for us for these rational functions. So again, I'd find domain. X cannot be 3. Set the denominator to 0 and solve. X cannot be 3, or all x values as long as x is not 3. I want to take a look at the numerator. I can factor that numerator maybe. Let's see. Two numbers that multiply together to give me 5 and add together to give me -4. It should be these two numbers. It doesn't really help me. I can't cancel anything out, or there's no like factors. So that means there's no holes. I do have a vertical asymptote by how we define it at x equals that bad value, x equals 3. There's no horizontal asymptote because the degree of the numerator is greater, but there will be a slant. There will be a slant asymptote here. And how do I find that? Well, let's take a look. F of x equals x squared minus 4x minus 5 over x minus 3. We learned we have to do long division again, or in this case we could do synthetic. Let's do synthetic. You can always do synthetic if you're dividing by a linear factor. So synthetic goes like this. Let's see what happens. Let's see if I can rewrite this guy like we did when we studied polynomials. Bring down the 1, multiply, add, multiply, remainder. Okay? So what I have here is the quotient is x minus x, right? Because I divided a quadratic by a linear. X minus 1, sorry. X minus 1. But it didn't go in evenly, which we're not really used to. So I can rewrite my function as x minus 1, right, the result, plus, so this function is equal to, the original function is the quotient, you remember this, it's the quotient plus the remainder over the divisor. And the divisor is just a constant, or a linear function in this case. I'm dividing by x minus 3. So this function, and it's going to look a little weird, is the same function as x minus 1, my quotient, plus the remainder, -8, over what I divided by, x minus 3. So what I'm telling you is that these are the same function. This function is the same as this if factored. The factoring didn't help us too much for this case. Is the same as that. Let's see if that is right. I'm going to graph both of those. X squared minus 4x minus 5. X squared minus 4x minus 5. And we divide it by x minus 1. Okay, so I get this weird looking thing. I can see my vertical asymptote. Let's zoom in a little bit. X equals 3. And what I'm telling you is it's the same thing as this thing. So let's take a look. X minus 1 plus this little rational function. X minus 1, x minus 1 plus, and then I had a -8 over the same divisor. Oh, sorry, this was an x minus 3. Try that again. Vertical asymptote x equals 3. That's better. And this is the same original denominator. Okay, can you see it's the same thing? The purple goes right on top of the green. So they are indeed the same function, and not only that, same function, but not only that, this x minus 1, let's see what happens when I graph x minus 1. X minus 1 becomes my slant asymptote. That's what happens as x goes to infinity. The result that is the quotient, that's a linear function, is the slant asymptote. The graph will hug that line as it goes to infinity and negative infinity. Okay, and as you might guess, that's really going to help us when we graph our function. All right, so when do I have a slant asymptote? That's the first thing, is recognition. When do I have it? When the degree of the numerator is 1 more than the degree of the denominator. How do I find it? I do long division and rewrite my function using this formula. And then this thing, the result, or the quotient of the division, is my slant asymptote. Slant. Y equals x minus 1. Okay? And then that's pretty much it for the new stuff. And then the old stuff would still be to find things like, well, what's the x-intercept? If there are any. What's the y-intercept? What's the range potential? That might be a tricky one. We'll talk a little bit about that. But if I have the x-intercepts, the y-intercepts, and the vertical asymptotes, the slant asymptotes, I should be able to get a pretty good graph of these things. Here's another one. Let's try example 4. So example 4, let's do all the things. So I say find all asymptotes. Find VAs, HAs, or let's call them SAs, slant asymptotes. First, we'd find the domain. Now remember, we don't always have all of these things. Sometimes we have a vertical, sometimes we have a horizontal, sometimes we don't. Sometimes we have a slant, sometimes we don't. Sometimes we have holes, sometimes we don't. So that's our job to figure that out. So the first thing I would do would be to factor and find the domain. Two numbers that multiply together to give you 30 and add together to give you 11 would be 5 and 6. So the domain is everything, all x values, as long as x is not -6 or -5. So then the question is, what happens here? Is this a hole or is this a vertical asymptote? In this case, they're both vertical asymptotes since there's no like factor above. So that is x equals, remember vertical lines have x equals constant equation. So I have two vertical asymptotes. And then I can find the horizontal asymptote, because there is one in this case. The degree of the denominator, 2, greater than the degree of the numerator, y equals 0. And now I can do a little bit more. What about the x-intercept? Remember, to find x-intercept, I take my function and set it to 0. So the idea here is 0 divided by any number is 0. So as long as my numerator is 0, and that result is in the domain of my function, I have an x-intercept. So I set my numerator to 0. That's how we find x-intercepts set for rational functions. I just set the numerator to 0 and solve. And that's pretty straightforward here. Happens when x equals 0. And if I were to plug that into my function, the y would be 0 as well. That's the origin. Okay. So I just added one property here. I find the x-intercept. Set your function to 0, which means I set my numerator to 0 and solve. That gives us a lot of information. The goal here is the graph. Let's see what I have so far. See if we're there yet. If I were to do a rough sketch of this thing, I know it passes through that point. Big idea here is that I have two vertical asymptotes, one at -6 and one right next door at -5. Okay, I know there's a horizontal asymptote. So what's going to have a horizontal asymptote at y equals 0, which is the x-axis. And I don't have any other points. But I have a pretty good idea of how these things act. It's going to horizontal asymptote was y equals 0. I have a pretty good idea of how these guys act, right? It's going to be, I'm not really sure what's happening here, but I know it's going to hug this line as I go through. As I go to positive infinity. Okay? So I don't know if I want to start with this one in terms of graphing. We'll come back to this. We'll come back to this one and graph it. We talked about these removable discontinuities are holes, what I call holes. All right? So I already talked about that. Find the point where the function's undefined and then check for common factors. If that's the case, you have a hole. Okay, so we already did that. I kind of led with that. So we found holes and horizontal asymptotes. All right, let's start with this one. I'll come back to that other problem because that one's a little complicated, but we'll come back to that one. Let's get some practice with maybe something a little bit easier. I want to start with I'll start with this one. Okay, let's start with an easier one. So let's do everything. Let's find the domain. I set the denominator to 0 and solve, so I'd have x plus 1 over x plus 1 times x minus 1. So the domain are all real values as long as x does not equal plus or minus 1. And from that I say, okay, what's happening at 1 and negative 1? Well, there's a like factor that goes with x plus 1, which is the 0x minus 1. So there's a hole then when x equals negative 1. Let's find that hole. G of x would be the simplified version, 1 over x minus 1. So that's 1 over negative 1 minus 1, or 1 over negative 2, negative 1 half. So I have a hole at negative 1 comma negative 1 half. I have a vertical asymptote for that, the 0 that corresponds with this bad value, or the value that's out of the domain here at x equals 1. I have a horizontal asymptote at y equals 0. This is that case where the degree of the denominator is greater than the degree of the numerator. So I got a lot of information here. Horizontal asymptote, y equals 0, that's the x-axis. Vertical asymptote, x equals 1. Oh, try that again. X equals 1. Oh, how about an x-intercept? Let's see if this thing crosses the x-axis. Well, remember, I told you to set your numerator to 0 and solve, and I'd get negative 1. But we got to be careful because that's not in the domain. So there are no x-intercepts. It will not cross the x-axis. Oh, what about the y-intercept? Y-intercept we get when we plug in 0. Just like always, any function, we plug in 0 for x. And that's 1 over negative 1 or negative 1. So there is your y-intercept. Okay? So now the graph's really formed by these asymptotes. I have really no choice. I know it's going to hug this line as I go back to infinity, and then this line as I come in, and has to cross this point. So I end up with that pretty good. And then I'm pretty sure it's going to do this, just based on looking at a couple of these. I'm pretty sure that's going to happen. And the only problem I have is I don't have my hole graphed. So if I were to graph my hole, which is a negative 1, negative 1 half, it should be, I want to leave like a little space right there for the hole. Okay? And I did a little bit of guessing just because of my knowledge of these functions. But if you want to be sure that this thing was up here, you could just do a quick test value like f of 2. Did I get f of 2 right? Well, f of 2 would be 2 plus 1. And then on the bottom, 2 squared minus 1. 2 squared is 4 minus 1 is 3. So actually f of 2 comma 1 is a point. So I missed it a little bit. It should be like that. But the point is that was a plus 1, and I knew that part of the graph was up there.